Okay, let's start with this second lecture. Now we know approximately how to assess the performance of a lot of different propulsion systems. The next step is to go a little bit more into compressible flows. But by compressible flows, we will mostly deal with internal flows, okay? Because we are more interested into engine than into the shape of aircraft, for example. And so the typical configuration of flow we will be interested in will be this one. And for some reason, I will get back into on the next session. And so most of the flows we will consider will be supposed to be one-dimensional, okay? Because it corresponds to the type of flow, the kind of flow which occur inside engines. And because this flow is flow of gas, and specifically because the specific velocities of these flows are really high, and specifically regarding to the speed of sound, but we need to talk about compressible flows. And so you already had the previous lecture of fluid mechanics last year, probably. It was only about incompressible flows. Okay, so you were supposing for most of your application that the density of the fluid was constant or almost constant. For this one, we will discover the specificities, the specific characteristic of compressible flows, because it's really needed to understand this if you want to understand how rocket engines, more specifically, but also aircraft engines are actually working. So just to start with a really simple example. Just imagine I produce some sound and I move at the same time, okay? So the sound, as you probably know, is just a disturbance of pressure in the air all around us. So if I say, oh, the sound will propagate at a speed which is close to, you know, approximately the speed of sound? 300 meters per second. You will produce some sound, and if you move, so you will displace, and for example, you imagine you have this initial position, and you are going into the next position, so you will produce some sound, and the disturbance of pressure that corresponds to the sound you just emit will propagate into the media, into the air, at a specific speed, which is usually really higher than the speed at which you are traveling. And so the times needed for you to cover this distance, the sound has already went to this. And so you travel again, and if you imagine, for example, you think about some pulse of sound, okay? It's not a complete, it's just a sound, bo, 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 and you have some pulse of pressure, okay? And this pulse of pressure will propagate and will create a sort of sphere. It's a sphere. In this case, it's obviously a two-dimensional graph drawing. It's just to get back on really simple signal of pressure. So you imagine you have this kind of signal of pressure which is traveling at a specific speed. On each time you are traveling and traveling, you will create a specific disturbance of pressure, but you will also displace you at a specific speed. Okay? And so if you are looking in this direction, the wavelength of the sound will not be the same if you are looking on the same direction. You know the name of this effect? It's really famous. Doppler effect. And for most of mechanics, on mechanical fluid mechanics, you already saw it's pretty much this, because you consider mostly liquids. On a liquid, the order of magnitude of the speed of sound is 2 kilometers per second. Okay, so it's really high. The sound is propagated really fast in this kind of dense media. And so, well, even if you have a really high speed in the flow of liquid, you will never reach this kind of situation when you have a really a strong disturbance of pressure. So if you are producing some sound and you are moving, because of the combination of these two phenomena, you will create a disturbance of the pressure field all around you. Now imagine two different situations. You have one situation when you are, for example, in a liquid, and so the speed of sound is really high regarding to the specific speed of the flow or the speed of the object inside the flow. Any kind of mechanical information can only be transmitted at most at the speed of sound. This is the definition of the speed of sound. It's the speed at which any kind of pressure disturbance is transported into any kind of media. So if I just take on this tennis ball, and I imagine I have, for example, my tennis ball, which is inside this kind of tube. Okay? And the speed of sound is really high against when regarding to the flow of speed, the speed of the flow. Okay, so you have some speed of the flow, and so you always have some influence from the wall. But the information about the influence from the wall is transmitted, is transported at the speed of sound. And so, for example, if the flow is arriving here, you will have a mechanical balance. For example, you will create some force because of the drag, and so you will have an influence of this. But the field of pressure will be quite homogeneous. Why? Because the time needed for a fluid particle to travel this distance, the speed of sound would make a lot of go way and back. Okay, and so you really have the time to exchange the information. Also, there is no actual disturbance. Okay, if I change something here, for example, I don't know, I just change the shape, it will create an information because I close, for example, a valve. You imagine a valve in any kind of fluid circuits. You close this valve, the speed at which the information is transmitted is equal to the speed of sound. And if this speed is really higher than the speed of the flow, you don't have any trouble with the speed of the flow. When you have this kind of trouble, sometimes it can appear, for example, if you have some valve which is really quickly closed, or you have some accident on some tube, and it's called hammer effect. In French, it's coup de bélier. And so this is the only situation when the speed of sound in a liquid is really is relevant regarding to the process you are working on. But for usual flow, you don't have this kind of trouble because the speed at which the flow is going is really lower than the one at which the information is transmitted. Imagine now a second situation where, for example, you are in a gas and the speed of the flow is of the same order of magnitude of the speed of the sound. There is absolutely no way for the ball, for example, to transmit any information faster than the speed of sound. Okay, it's impossible to do so. So imagine if the flow of the fluid, if the speed of the fluid is the same as the speed of the sound. It means it's impossible for the ball to just transmit information with its neighborhood, with its surrounding, okay? Because the time needed for a fluid particle to travel this distance, you just have one way. But the time needed to have the back, in order to equilibrate the pressure, the fluid is already here. And so in this case, you will create a lot of disturbance, and you will create really sharp variation of pressure, because the system doesn't have enough time to just equilibrate its pressure, to just have an homogeneous pressure. It's impossible to do so. It's too fast for it. Another image, for example, imagine you want to swim, and you swim in a river, and you swim exactly at the speed of the river. You won't go forward. It's impossible to do so, because the time you will go on, you will just go forward, you will receive exactly the same amount of fluid from the river. It's exactly the same for this. And so, when the speed of the fluid is close to the speed of sound, you can sometimes have some really sharp of brutal phenomena, which is called shock wave. And so, because it's impossible for the ball to just equilibrate its pressure for the surrounding, because the information is just blocked by the speed at which the flow is arriving, you will create a shock wave. And this shock wave, it's an extreme situation. Sometimes we don't have this kind of phenomenon. But this shock wave corresponds to a violent, a really brutal change of the density of the flow. And so this really nice hypothesis is not usable anymore. Because at some point, because you have a really strong variation of pressure, gradient of pressure are really high, also at the same time the gradient of density. And so your flow is not incompressible. It's compressible because at some point the density of the fluid is really different from the one at another location. And when the speed of sound is close to the one of the flow, you start to have some trouble because you will create a lot of variation of pressure and so of density. And so your flow is not incompressible anymore. Incompressible flow means that the pressure disturbance have enough time to equilibrate itself inside the flow in order to have a gradient of pressure which is quite smooth, okay, quite low, because you don't have a really sharp variation of pressure. In compressible flows, you don't have this time, okay? There is no time for the information to be exchanged, and so the only solution, the only final situation, which is just created by the laws of mechanics, is the creation of this shock wave. And to a shock wave corresponds to a strong variation of pressure, density, temperature, velocity, and so on. And this kind of phenomena are really complicated. Don't make the confusion between incompressible flows and incompressible fluids. For example, if I consider some air, I just imagine I have, I don't know, a wind turbine, for example. Okay? A lovely wind turbine. It's not a flower, it's a wind turbine. No, it's not a flower. Okay? You have your wind turbine and you have the speed of the wind. And you know that the speed of the wind is, okay, 40 kilometers per hour. But the speed of sound in this unit is really larger than this. So it means that even if your flow is of air, and air is supposed to be a compressible flow, a compressible fluid, the flow, the resulting flow in this application is incompressible because the speed of the flow is really lower than the speed of sound, even if you have a gas. And so in this case, your fluid is compressible, but your flow is not. So incompressible flows means liquid on gas at low speed, but compressible flows usually means compressible fluids, but with high speed or speed which are close or even larger than the speed of sound. And so if I just take a look more locally on what happens inside this kind of shock wave, I will have a concentration, a strong variation. And it's really strong because if you want to measure the thickness of this variation of pressure, the order of magnitude is 1 micrometer. So it's really small. It's almost nothing. But in this micrometer, sometimes you have variation of pressure of hundreds of bars. You have variation of temperature, sometimes of thousands of degrees. So it is really violent. And it is exactly the kind of process that is used for bombs, for example. When you have some kind of explosion, the goal of this explosion is to increase locally the pressure to create this pressure wave. On this pressure wave, this shock wave, when it's propagated, it's used to destroy something. Okay. Also some other example of this kind of shock wave for two different objects. So this one is a sphere or a cylinder, I don't know exactly, probably it's just a cylinder. And this one corresponds to another kind of shape. And if you change the shape, you will also slightly change the shape of the shock wave, because you always have this kind of equilibrium that will create from the object to the shock wave and from the shock wave to the outside. I will get back on the Mach number just after that, but Mach number means that the speed of the flow is 1.5 the speed of sound. Other example for more complicated shapes, some shapes that are really close to the one of vehicles. This one is quite simple because it's just a sort of triangle, but it creates a lot of shock waves with a really complicated shapes and structure. You will create a first shock wave that corresponds to the nose, okay? The first part of this, and you will create a first change of pressure. You have another one, and you have a lot of shock waves that are created everywhere after that, okay? And it's called shock diamonds because usually it makes some diamond shape or diamond structure. Even more complicated, so a small model of the space shuttle. The structure of the shock wave are even more complicated because the shape of the vehicle by itself is even more complicated. And if you have this kind of pressure disturbance, it also means you will expend a lot of energy in order to keep the motion. Okay? It's not only about drag. You already heard about drag during your first lecture of fluid mechanics. This one it's another effect of drag. It's not about it's not about viscosity or friction inside the fluid. It's only about the mechanical energy which is dissipated by this shock wave. Another example of diamond, I will get back on the Blackbird later, but you have the flame which is getting out of this engine. Also, you have the flame which is created by the engine. In this case, because the pressure at the outlet of the engine is really higher than the one at the outside, the only way to equilibrate the pressure is to create this kind of shock wave. If you consider, for example, this outlet of engines, and it's really typical if you're looking at some old movies, as for example, Top Gun. It's too old for you? It's enough. Oh, thank you. You're kind. Anyway, you have this kind of outlet area, and because the pressure here, PE, is larger than the atmospheric pressure, the only way you can have to equilibrate your pressure at the end is to create this kind of shock wave. And so you have this. It's why it's called diamond, because you will have this kind of structure. It's beautiful, but it's really complicated to draw. And so this is the way you have different shock wave, and you have, for example, pressure P1, P2, which is here, and you have another shock wave, P3 here, P4, and so all of this structure corresponds to a decrease of pressure until you reach the final one. And this picture corresponds to a test on the bench for the same engine. So just imagine the temperature of the body of the engine, considering this color. Don't touch, it means. And another example, probably when we look at the slides on your laptop, it will be clearer. What happens when there's an explosion? you have this kind of shock wave. In this case, it's possible to directly see it because the variation of density means also a variation of the optical property of air. And so the light is not traveling exactly the same way if you change the density of the air. It's exactly for this reason that it's possible to see the shape of this shock wave. On actual time, you have the explosion, and you have the speed of the shock wave, and when you are really at a larger distance, you say, no, it's okay, and you just have the time to just hide you and let the pressure wave go just above you. It's really interesting. Anyway, if I get back on my ratio, it's really easy to understand that the main properties, the main parameter that will correspond to a specific behavior of the flow is the Mach number. So Mach number is just a dimensionless parameter that corresponds to the ratio of the typical velocity of the process. So it can be, for example, the velocity of the object. It can also be the velocity of the flow. It will happen, for example, in our engine. At some point, we will have some specific value of the Mach number. So it's a typical velocity, exactly the same, for example, you used in your Reynolds number. You remember this? It's exactly the same for the Mach number. It's a specific velocity that could be, for example, the average one, and you divide by the speed of sound. Okay, so it's another dimensionless parameter, and it plays pretty much the same role as the Reynolds number, but for compressible flows. Okay, I will explain later that when the Mach number is really high, usually friction effect on viscosity can be completely negligible. It doesn't exist, or the effect is really insignificant regarding to other effects. Also, in this case, it's possible to describe the complete behavior of the flow considering almost only this. There is another properties of the gas, but the main parameter of the flow is the Mach number. Right? The third part of the lecture. Most of the example on application we will talk about in this lecture are actually coming from military application, because the armies were the first to be interested into such kind of flow. For artillery, for fire bullets. Also, the German works on this, on Mach, for example, Ernst Mach. The Mach number comes from his name, has also contributed to this kind of work. And he took this first picture of a bullet at the end of the 19th century. So this kind of experiment is quite impressive because it's really old, and it was possible to see this kind of shock wave that was produced by the bullet. If I'm not wrong, this line just corresponds to some kind of default of the optical system. It's not really related to the physics of the flow. First days, and the second days was about aeronautics, and specifically aircraft or planes, because when the first planes have been tried, nobody knows exactly how the lift was working. So these guys works a lot on specifically during the Second World War, because they wanted to try some faster military aircraft. Okay, and probably you know that the first who test this kind of aircraft was German, so the Nazis during the Second World War, but it didn't work, hopefully for us anyway. The third days corresponds to the Cold War, and it's even more complicated because it's about two different applications of compressible flows. The space programs, and specifically the change from the atmosphere to space, because when you are getting back from space to atmosphere, you have a really strong increase of density in a relatively short length. And also about atomic bombs, because atomic bombs are also producing a lot of this complicated process that are called hypersonic. But I will try to stay more on the side of the space program than on the side of atomic bomb. I'm a peaceful guy. Now it's possible to create a sort of classification of different kind of flows. The first one you already know is incompressible flows. Incompressible flows means that your Mach number is lower than 0.3. Okay, even for air, 0.3, you can suppose you don't have a lot of variation of density. So you can neglect this. And after that, you have the subsonic part. Okay, subsonic part means all of my flow is subsonic. I have some variation of density, so significant variation of density. So maybe I will have to make some calculation in order to compute this variation of density, but it's still subsonic. So the speed everywhere in this flow is lower than the speed of sound. And then you have the complicated part, because it's the transonic part. Transonic part means some location inside the flow, some part of the flow are supersonic, and some other one are subsonic. And the transition from supersonic to subsonic is always with a shock wave. And so it means you will have some disturbance of pressure at some point, because at some specific location, for example, above the aircraft is supersonic, but below is subsonic. And this is exactly the reason why it's really complicated to fly in this range of Mach number, because you will have a lot of troubles with vibration and variation of pressure. The speed of sound is here. Okay, by definition, the sound barrier. The sound barrier is here. By definition, it corresponds to the level at which you are just flying above the speed of sound. But it's not the end of troubles. Okay? And the end of troubles usually is close to 1.2 Mach number. Above this value, all of the flow is supersonic. Okay, so you maybe have some troubles, you have some strong variation of density, but you don't have this vibration on brutal change of pressure anymore. So you are not flying this way. You are flying in another way. And it's why supersonic flights are always higher than 1. The Concorde was at 2.2, something like that. And the trouble appears here in hypersonic. So hypersonic means it does not mean you have really high speed. It means that you have a really low value of the speed of sound. The Mach number is this. So this Mach number can increase a lot just if your speed of sound is decreasing. And the speed of sound is broadly proportional to the density of the fluid, of the air. And so if you increase your altitude, you will decrease your density, and so you will decrease the speed of sound, and with the same speed, you will increase your Mach number. The heat barrier is when your variation of pressure and density is creating a large variation of temperature. And so you can just cook your vehicle, because the increase of temperature is completely crazy. And this is the reason why spacecraft are using heat shields, okay, that are designed in order to just protect this spacecraft from this increase of temperature. So what a transonic example of a transonic flows, it creates instabilities, because, for example, all of this part above this wing corresponds to a subsonic flow, and you only have some supersonic zone here. On the separation between the supersonic and the subsonic must be a shock wave. So you will create this kind of shock wave above your wings, and you will also create the vibration that corresponds. So it's a really uncomfortable situation. The same here, if your Mach number is lower than 1.2, broadly, because it obviously depends on the very configuration of the flow, you will have a subsonic zone just in the front of the wing on a supersonic here. And so you will create a first shock wave and a second shock wave here. And these shock waves are responsible for this variation of pressure that will create a lot of mechanical constraints of the aircraft. It's why we need to avoid this zone as far as possible. If you want to go to supersonic, do it the faster you can, to avoid this kind of pressure disturbance that maybe will just destroy your aircraft. Quickly, for some reason I will not go into because I don't have a lot of time for so, there's a really simple idea and demonstration that show that when you increase the Reynolds number in a really large value, because you increase the speed at which you are flying or the speed at which the fluid is flowing, you will also decrease the viscosity effect. Okay, so there is no boundary layer, there is no friction, there is no, all of this kind can be completely neglected. Okay, it's completely insignificant in this case. The origin of the dissipation process are completely different, but it's not about friction. Okay, so it's exactly why we will suppose that these flows are ideal from the friction point of view. Okay, no friction. Okay, if I take a look at some, for example, the value of the speed of sound. You have the speed of sound. This one is in kilometers, so its altitude, for example, a commercial aircraft is this way. The limit of space is just here. We suppose the limit of space is here. The structure of the atmosphere is more complicated than we would imagine. Okay, if you increase the altitude, you will decrease the speed of sound because the density of temperature is decreasing. So for the same speed, you will increase your Mach number. Okay, so it's why when you have, for example, some news about a completely new aircraft that flies at Mach number 5, first question is, okay, but at which altitude? Because Mach number 5 at 80 kilometers, it's not really complicated, but to do so at 10 kilometers, it's another story. Okay, so the speed of sound is decreasing. After that, it's the same, and it increases, and it decreases, and so on. So depending on the altitude, we have some kind of correlation, standard correlation we can use in order to compute the value of the speed of sound. And this one is called mean free path. Maybe you know what it is. It is the mean distance any molecule travel between two successive shocks with another molecule. So at the density of the air all around us, the mean free path is of the order of magnitude of 1/100 of a micrometer. Okay, it's close to the nanometer. And so a molecule, for example, of nitrogen all around us will travel on the average 1 nanometer just before knocking to another particle and so on. So it's really close. But if you are decreasing the density, you will also increase the mean free path. And if you are going into space, so space is here for us, it's 100 kilometers, a molecule will travel for almost 10 meters or 100 meters before knocking to another one. So it's vacuum. It's not really vacuum. It's almost vacuum. And if you increase again your altitude, for example, to 1,000 kilometers, in this case, just look at this. The mean free path of a molecule is 1,000 kilometers before knocking to another particle. So yes, now it's really vacuum. So the hypothesis we will use in the rest, I will explain this shortly because we will use a lot of this relation after that, is just for you to keep in mind the limits of our calculation, because we'll use quite simple relation, but this simple relation cannot be used for any kind of application. They have their own limits. And so the first limit, we suppose that our flow are stationary. So we won't work on explosion where the shock wave is just traveling at a specific speed. This kind of example won't be considered. We suppose we don't have any friction, and it works good for most of application. We suppose that our gas are lightweight, so all the effect of gravity are completely insignificant. All the flows are one-dimensional, so we suppose it's in only one direction. If I show you some picture of two-dimensional or three-dimensional flows, for this lecture, it's enough to understand how it works in only one direction. Gas are supposed to be perfect. Perfect gas, it's clear or not? Ideal gas, probably it is. What does mean ideal gas? It can be described by the ideal gas law, okay? Ideal gas means pressure and volume are related by this kind of relation. Pressure, volume, mass, and temperature. Perfect gas means that plus an hypothesis of constant values of specific heat. So constant values of specific heat at constant volume and at constant pressure. Okay? They are not supposed to depend on temperature. And so if you combine these two hypotheses, you have a perfect gas. Perfect gas means ideal plus constant specific heat. And after that, no chemical change in the flow field. So we won't go into the details of the combustion process inside rocket engines because it's a nightmare. No magnetic or electrical fields effects. Magnetic or electric fields or effects can appear, for example, when you are just getting back into the atmosphere, because the highest part of the atmosphere is the plasma. The electric field, the electric effect are really, really strong. And if you are studying the flight of spacecraft specifically in this zone, you need to take this into account. And so this one is quite quick because it's only about the hypothesis I already mentioned about the gas. We will just consider air with this kind of properties. So all the examples for today are related to air, but in next application, probably we will consider other examples of gas flows. For example, the one of exhaust of combustion process in a rocket engine. So this one, not complicated. Only 3 questions to describe the behavior of all of this flow, considering this hypothesis. The first one is the conservation of mass. So continuity equation, I'm pretty sure you already heard about that. But in most of your application, you were not considered this relative variation of density. It wasn't considered. You just suppose your flow was incompressible. And so when you decrease the cross area of the fluid, you will increase the speed. Okay? Venturi effect. Anyway, the continuity equation can be written as the sum of this relative variation, so cross area and density, is equal to 0. Okay, it's just a conservation of mass, but we suppose that the speed can change, the area can change, because if we have, for example, a throat or a nozzle, the structure of a nozzle, it corresponds to a change, a specifically designed change of the cross-section of the flow. Okay, so in this case, you have a cross area which is changing, the speed is changing, but the density is changing as well, because your speed is close to the speed of sound. After that, the second relation is related to the conservation of momentum. So I know it's impossible to read, but you will have this on your slides. And so with this, conservation of momentum means that your variation of kinetic energy, so it's mass-specific kinetic energy, because it's the kinetic energy but divided by the mass of gas involved, is related to this ratio. It's dP, yes, over rho. Okay, it's the variation of pressure divided by density. Sum of the momentum the variation of momentum corresponds to the sum of force gives this. On the last one corresponds to a variation of energy. So the variation of momentum, here, if you integrate the equation of momentum, you obtain a variation of kinetic energy. So if you want to change the kinetic energy of your flow, you will need to produce some work, and it corresponds to a work on compression. In fluid mechanics, when you made some calculation about pumps or this kind of device, you were considering that the density was a constant because it's an incompressible flow. And so the density is getting out of the integral. And so the work of compression is just this. And it's exactly the formula we use to calculate the consumption of mechanical energy or mechanical power from a pump of liquid. But if you want to do the same calculation for a compressor of gas, it's this, because in the meanwhile, from 1 to 2, you will have a variation of density. And now the last equation to describe this is the equation of energy. So conservation of mass, conservation of momentum. The last one is the conservation of energy. And in this case, when we are doing the complete calculation, we obtain a variation of what is called the total enthalpy. So sometimes it's not this, but actually total enthalpy means just the enthalpy of thermodynamics, the usual one. So broadly, the thermal energy which is contained into the gas, plus the kinetic energy. Okay? And this variation of total enthalpy is just the relative amount of heat that has been supplied to the gas. Okay? So if you heat up some gas, you will increase the temperature, but it's also possible to increase the kinetic energy of the gas, of the flow. And so if you want to describe this kind of flow, you always have to manage these three relations at the same time. But hopefully we won't do so, because we have other relations that combine everything in the same formula, and it's really easier this way. And once again, all of this equation only for stationary, one-dimensional, ideal gas, and so on, invested on all the hypotheses we previously mentioned. Now we will suppose most of the application we will deal with are these ones. In this one, we suppose that the flow is mostly isentropic. So you mean isentropic means no friction, no dissipation process, and no heat exchange at the same time. Okay? But actually, the isentropic zone of the flow is all of this. The only location, but really small, corresponds to a small volume in the flow, where the flow is not really isentropic, correspond in this case to boundary layers. Okay? But if we suppose we can neglect the effect of boundary layers because there is no significant friction, we suppose the complete flow is isentropic. And this is the reason why we will do all the calculation supposing the entropy of the flow is maintained, remains the same. Okay? There is no friction, no heat effect. It's a strong hypothesis, but it works quite good if you compare with some experimental result. In the specific case of an external flow, for example, all around a bullet or a rocket or anything else like this, the only zone where you don't have the isentropic flow corresponds to the shock wave, because you have a production of entropy in the shock wave. And also on this shock wave, on the friction all around the body of the bullet, and probably also in the wake which creates the drag effect. Okay? But for us, it's not really the main point of our explanation. We are more interested into this kind of flows. And I will probably have some time to finish. The effect of compressibility, so the possibility to have a density that varies, is related only to Mach number. With this kind of relation, it's not complicated to demonstrate it. For any value of the Mach number, which is close to 0, so the speed of the flow, which is really lower than the speed of sound, we can suppose we don't have any variation of density. So it's exactly what I explained at the beginning of the lecture. Now it's based on mathematics. When the Mach number is equal to 1, is close to 1, so it's really close to the sound barrier, you have a relative variation of density, which is at the same order of magnitude of the variation of speed. Okay, so you have a decrease, for example, of velocity, you will have an increase of density of the same magnitude. And if you are in a supersonic flow, because it's to the square, so you will have a stronger variation of density, which is due to the same variation of speed. Okay, so you decrease the speed a little bit, but you will have a larger value of the density. And this is the reason why you will have some shock wave that will appear in your flow. So conventionally, we suppose that the flow is compressible, so we don't mind about any variation of density as long as the Mach number is lower than 0.3. And it's the same in industry. The calculation in industrial context are using exactly the same limit. And so if I combine everything and I save you a lot of pain and sweat because this calculation is quite long, it's possible to rely any kind of parameter. So a few minutes of light, and after that it's over. We are considering this kind of flow, so one-dimensional flow, any kind of shape. Okay, so you can imagine you have this. Well, try to put something symmetrical. Okay, so something absolutely ugly. Anyway, if all the previous hypotheses are applied in the same way to this flow, because you suppose the main direction of the flow is this, and you put at any location, for example, this location is node 1, or this location is node 2, and you know for this location, for example, the specific area of the flow, it's possible combining all the relation to rely the pressure, the temperature, and the density of the fluid just with this kind of relation. And it's really easy to use because if you take a look at this relation, they are only taking into account the Mach number at two specific points. So you imagine you have the Mach number at point 1 and the one at point 2. Because it's a perfect gas, we suppose that Cp and Cv, the specific heat, are constant, and so the gamma, which is the isentropic exponent, the heat capacity ratio, is a constant, and so the ratio of pressure, temperature, and density are only related to these two Mach numbers and a function of this gamma. And so if you know the gamma and you know the Mach number, you can calculate everything. Pressure, density, temperature, and so mass flow rate, and everything. Okay? On all the calculation we will do in the rest, specifically the one of thrusters, we want to, for example, calculate the specific areas of a nozzle in order to produce some thrust, all will be related to this. And I finished. This one is only about what to remember on some reference, and I'm right on time.